Up until now, we always looked at the classification problem as having only two classes. That's why we called it binary classification problem. There are many situations that in modeling practice where you need to work with more than two classes. And those problems belong to the multinomial classification domain. In other words, that's the situation when instead of predicting just one of the two target classes, you are faced with k target classes. So for example, you have a survey forms, and on the survey form, the performance can be evaluated as either high, medium, or low. So in this case, you have three classes. Or suppose you want to classify different types of images, and you have more than two different categories of images. So the multinomial classification is the most general classification problem that arises out there, and therefore it requires a very special care in terms of how its performance can be evaluated. Now, at looking at all of the different approaches to multinomial classification, you'll discover that there are basically two key distinct approaches. In the first approach, we are focusing on the performance of a classification model as it classifies classes to one type or another. And that usually brings us to the concept of expected cost, and this is the topic of this video. So in other words, we don't really talk about predicted probabilities or log odds or likelihood or any kind of phenomena like that. The second approach is more strict, and that is the approach where we're actually asking our model not just classify records to one of the k classes, but to make to generate predicted probability of each individual class. And those types of models, they can be evaluated in terms of average log likelihood or margin or the other concepts like that, and they are discussed in a follow-up video. But before we get there, let's just focus on the classificational side of the story and see how it can be summarized. So what I have here is, usually we start with some kind of population. So this is my population here. And we're assuming that we have basically k target classes, k greater than 2. So the simplest case will be k equals 3. So I have the population members belonging to class 1 or class 2 or class 3. Now, what usually happens, we don't have access to the entire population, so you're looking at it by way of drawing a data set. So you have access to some kind of modeling data set. And this data set also has records partitioned into N1 records belonging to class 1, N2 records belonging to class 2, and N3 records belonging to class 3. And these are capital N's. Now, one important characteristic of the data set is that it may or may not be a true snapshot of the population. And in order to introduce that concept into the picture here, what's usually done is we introduce a vector of prior probabilities where j goes from 1 to k. And this vector of prior probabilities kind of shows us the expected or targeted distribution of classes in the population. So we detach population from the data set. So in the data set, for example, you could have class N1 oversampled, whereas so it would have a half of the records belong to class N1, but in the population, class 1 is actually a real minority class, and so on and so forth. And it happens all the time. Sometimes you have access to records that were more available for one class versus another, and you always want to have that correction somehow communicated to the evaluator. Okay, based on the data, you build a model. At this point, it is irrelevant how the model is constructed. The point is that at each available observation, and we know the class that it belongs to, the model makes the predicted class assignment. So for every actual class assignment, in my case 1, 2, and 3, the model can predict either 1 or 2 or 3. And if you have a correct prediction, you'll be on the diagonal here. So class 2 predicted as class 2. If you have incorrect prediction, you have all of those possible events that can happen. And again, let's remember in general what is going on here. So if this is my data set indexed by 1, 2, 3, etc., n observations, and I know that those records are partitioned into n1, n2, and n3, of course I have x here, that's my predictors, and at this point the predictors are used somehow by the model in order to make the predictions. But I also have observed values. So my y's here, let's say set to 1, 1, 2, 3, 3, 2, 1, 2. So suppose these are my observed classes. Now the model somehow uses my axes, and it could be as simple as separating hyperplanes or individual logits. I mean, it doesn't matter. The point is that the model assigns each record in my data set to a predicted class y hat. And suppose you have 1, 2, 3, 2, 3, 2, 1, 1. So each record can be either assigned to the correct class or it can be misclassified. And it is instructive to gather up the statistics or to count up all of these different misclassifications and correct classifications that can take place. This is what's done in the prediction success table here. PST stands for prediction success table. Sometimes it's also known as confusion matrix, but it's kind of a confusing term and it's best to be avoided. Now the prediction success table will have all of these cells filled up with integer numbers, n11, n12, n13, n21, n22, n23, n31, n32, n33, where each individual cell, let's call it n, k, j, that's simply the number of observations in the data set that belong to actual class j but were misclassified as class k. And of course, on the main diagonal we have the desirable events. On all of the off-diagonal elements you have all of your errors. So the prediction success table communicates the classification performance of the given model on the given data set, whereas the prior probabilities communicate the relationship between the data set and the population out there. Now the question is, how do we compress this performance down to a single number so that we can compare performance of two different models? This is where analyst comes in place. So this is you here. And the way it is done is you can introduce a table of the same dimensionality, k by k, where in each cell corresponds to the possible event that may happen, and it's assigned to a specific cost. So you have a cost of misclassifying class 1 as 1, which is really not a misclassification, it's a true event. Then you have C12, C13, C21, C22, C23, C31. Let me do a little bit of nicer job here. Okay, so you have a C31, C32, C33. And the cells here, C, K, J, that's the user-assigned cost of misclassifying through class J as the class K. Okay, so these cells can be one-to-one mapped to the entries in the prediction success table, and that's the essence of the cost matrix. Now what usually happens though is that in reality you don't assign any costs to correct classifications, so these are zeros. and you assign some positive costs to all of these other misclassifications that can take place. There is really no rule on how the costs should be assigned, because it all depends on the nature of the problem that you're solving and your own characteristics. So it's a kind of subjective measure imposed by the analyst onto this problem. So you could say, for example, that misclassifying 3 as 1 is very bad, but 2 as 1 is okay. So you can make symmetric costs, non-symmetric costs, all sorts of different structures are available out there. So now we've introduced all of the 3 components. So we have a prediction success table, the model performance on the data that we have access to, the relationship between data and the population by way of priors, and also the suggested requirements by the analyst in the form of a cost matrix. We take all of those 3 components, and that allows us to wrap the entries from the prediction success table down to a single number. And the way it's done, you're essentially taking that fraction, you multiply it by the corresponding cost, and you multiply it by the corresponding prior. So all those 3 enter here. And again, it's instructive to look at general what the formula is trying to do here. First of all, notice it's a double sum. So we're summing up all of the cells here. And of course, for that special case when costs on the domain diagonal are zeros, that means that terms that correspond to the main diagonal will vanish. But otherwise, for each cell, you take the fraction of that cell with respect to n sub j. And again, it is instructive to remember that if you take the sum of all of these individual counts in this column, then this basically gives you the total count of class 1 records in the data set. This sum gives you total class, column sum gives you total class of n2 records, and this is n3 records. Okay, so this ratio here shows the fraction of records from within the current class under consideration that was misclassified as one of these other classes. This event is multiplied by cost of the corresponding cell, multiplied by prior to kind of change, to offset the performance on the data towards the population. And the nth thing is averaged to give us the so-called expected cost. And the expected cost, that's EC here. Now, how one could interpret expected cost. Suppose you have your model, you have your population, and suppose you're drawing records from the population at random. So random draws. So you're making random draws, you're applying your model, the random draw belongs to a class according to that distribution of priors, and it lands into one of those cells. Each cell is associated with the associated cost. So whenever you apply your model to the sequence of random draws from the population where classes are presented by these priors, you will end up these random events. Each event has its cost. The expected cost happens to be the average of those, and this formula here gives you a direct and nice estimator of that expected cost based on the observed model performance on the given data set. And that's what we basically denote here as the expected cost. And of course, we want to minimize the expected cost, and that's kind of the ultimate goal of building our model. Now, whenever you calculate the expected cost, it gives you back a number. And I mean, you can use that number to compare performance of different models, but it's just like in regression, it would be nice to know what would be the worst case scenario. What's the expected cost that would be the cost of a no model at all? And that is something that we are going to call as the baseline expected cost. Now, in order to understand the baseline in the multinomial sense, we need to understand the following thing. That is, the worst case scenario when you have no model at all, you could basically consider trivial models that assign all records to a specific class. Well, to be precise here, let me just do a little bit of a cleanup here and basically elaborate on this. Suppose my baseline model is the model that makes everyone predicts as class 1. So in this case, all of my cells, all of my N1 class 1 actual records are assigned to class 1, but all N2 class 2 records are also assigned to class 1, and all N3 records assigned to class 1. So the remaining record cells will be zeros. So that's my trivial model here. And therefore, I can use this prediction success table of a J1 model and push it through the expected cost calculation, and this will give me the expected cost associated with trivial model class 1. Likewise, I could redo this and see what happens if I were to assign every record to class 2. So now my prediction success table would look like this. And again, I can take that prediction success table and put it through this formula and calculate the expected cost of baseline 2. So that was a baseline 1, and this is a baseline 2. And in a similar way, I can also calculate the expected cost of assigning everyone to baseline 3. And then if I I always want to minimize expected costs, so I have 3 alternative baseline models, so I can always take the smallest of these, take the minimum of all of these JB, and that becomes my expected cost baseline. So XE baseline will be essentially the minimum over J of the expected costs B when everybody is assigned to class J, and that gives me my baseline cost, or the expected cost of a kind of the worst case scenario when I'm forced to assign everyone to one specific class. Now this introduction of baseline cost gives now me the luxury of introducing a relative cost measure, which is simply the ratio of the current observed expected cost as a fraction of the baseline expected cost. And this relative cost has a useful range between 0 and 1, even though technically it could go above 1, and it would indicate that you're giving a model that has the expected cost that is worse than the baseline. But otherwise, it kind of shows you the fraction of the relative cost that remains unexplained, and it's kind of similar to some of these R-squared concepts, or more precisely 1 minus R-squared concepts that you will find in regression out there. Now when you look at the performance of CART models in SPM, you will see that at the bottom of the navigator it shows relative cost, and that relative cost is calculated precisely based on all of these considerations. Okay, now to round things up, let's do one final comment here. And that is, what happens when your cost matrix has a very trivial structure? Namely, we call it unit costs. Meaning all the cost of every possible misclassification is set to 1. So all of them are kind of equal. So what happens in this case is that this term becomes 1, so it disappears. Now the off-diagonal elements also disappear. The diagonal elements also disappear, so the summation now over all j not equals to k. And again, if I do a little bit of cleaning up here, what happens in this case is essentially these are 1s. And now it all boils down to the selection of prior probabilities. And in practical scenarios, there are 2 different ways to select prior probabilities. The number 1 way is the selection of priors that is set to the data-driven fractions of classes. And that is essentially a mathematical way to say that the data set was randomly drawn from the population with the given set of priors. So when you look at the data set, you use the data set to evaluate the population priors, and that kind of is essentially an approach when the data set is a snapshot of the population. Well, if you do that assumption here and plug it into this formula, so instead of this prior, you'll get essentially this n sub j over n. These terms cancel and can be pulled out. And what you have here is the sum over all off-diagonal elements of these elements. And what you're doing here is essentially looking at the fraction of all misclassifications divided by total number of records in the data set. And this is what is known the overall classification error, the classification error that ignores individual class assignments. Okay, an alternative approach would be when you basically assign priors to priors equal. And again, the costs are either 0 or 1, so that goes j naught equals to k. But this time, priors are set to 1 over k. Well, you pull 1 over k out of the sum here. And now if you observe what happens inside, you're basically looking at the focusing on class J and focusing on events where class J is misclassified as class K. So for example, this event and this event here. So you add these two up and you divide by the class J size by N1 or N2 or N3. So to make a long story short, if you look at this, you'll eventually convince yourself that priors equal gives you the expected cost that is essentially average classification error, meaning instead of looking at the overall misclassification, now I look at what happens in individual classes. So I take the misclassification within each class and then take the average of those k misclassification rates. And that gives you two very useful cases. And of course, average classification error is useful when you have disbalance in your classes and when you really want to make sure that the minority class is not overlooked, whereas the overall classification error is dominated by the major class. And as you can see, we essentially came up with a way to calculate a very useful measure, the measure of expected cost of a classifier. We didn't use any probability assumptions. We didn't use any response surfaces. We kind of assumed that we have a classifier that knows how to assign records to one class or another, and we have k of those classes. We managed to link things like priors that relate data set with the population, the model performance on the data set, and also n-list supplied requirements in the form of costs. And based on those, you can calculate expected cost, and more usefully, you can get the relative expected cost. And we also looked at some ways that this entire structure can be simplified to generally well-accepted terms like overall misclassification or average within class misclassification. In what follows, we're going to introduce the probabilistic side of the story, and that will lead us to yet another set of performance evaluation criteria that are typically used in the multinomial setting.